Hello back. It is time to talk about polypeptide synthesis or just peptide synthesis. All right, so let's pretend that we're interested in synthesizing DAN, right? So this is the tripeptide that contains aspartic acid, alanine, and asparagine. So what you want to do first is draw those amino acids, right? So you have aspartic acid, but notice here that I am bringing aspartic acids in the form of an ester. That's because I do not want the side chain carboxylic acid to be confused for the other carboxylic acid of the amino acid chain in the synthesis process, right? So I don't want side chain to get involved in the chemistry. So it has to be protected as an ester. Then we have alanine, which is just neutral, polar, uh, non-polar chain, excuse me. And then we have asparagine, which is an amide, which is not going to really get involved in the synthesis as far as the reactivity goes. All right, now the next thing is that we want to figure out what we're going to protect at the amino group and what we're going to protect at the carbonyl group. So since aspartic acid is going to be the first amino acid, we don't want anything prior to it. So that means that we're going to protect the amino group of aspartic acid, but we're going to leave the carboxylic acid intact. All right, at the same time, for alanine, we will want to have the amino group available so that we can actually couple these two things together, but we don't want the carboxylic acid end of alanine to be free, because if it is, we will have a problem of potential a cross reaction taking place. And the same thing is true for the final amino acid. We will want to have that amino group of asparagine free, but we don't want the carboxylic acid available. So what you will then do is you will activate the first amino acid for reaction. So you activate the carboxylic acid by adding DCC. And once this is activated, you'll react it with the second amino acid that has the amino group free. So you will have these two things reacting with each other. You will produce your dipeptide right at that point, and you'll also have as a byproduct dicyclohexyl urea. All right, then the molecule here will have to be deprotected. Now you'll have to use acid to remove the carboxylic acid. Now I'll be honest with you. This is not the best proposal for the synthesis because the second carboxylic acid of aspartic acid will also get turned into carboxylic acid. So this will not be the way to do it. In reality, you will want to use a different functional group for this carboxylic acid for it not to be deprotected at this point. So just keep that in mind. I'm gonna get to that momentarily. All right, but assuming that we have a different functional group so that this doesn't get deprotected, what you would have to do now is activate the second carboxylic acid that we have, the one of alanine with DCC, and you will then introduce the third amino acid, which will be asparagine, and these two things will get coupled together. All right, so you'll also produce dicyclohexyl urea in the process, along with your tripeptide. And so what you do at this point, now that you've synthesized the desired amino acid chain, the desired oligopeptide, you will remove the FMOC protecting group by adding piperidine. This will create fluorine. This will create CO2 as a byproduct. You will have the amino group of aspartic acid free, and then you deprotect the acids by doing pretty much treatment with H3O plus to remove both of those components. Like I said before, it would have been a bad idea to have a methyl ester for both this carboxylic acid and the one of alanine at the beginning process. So that means that alanine will probably need a different functional group for this to work out. But that's kind of how you would do this. Now, aside from the the little mistake I just highlighted right here with aspartic acid, there's a couple of drawbacks. The first one is that as you go through the reaction, you're changing the pH constantly because at certain times you need to add a base and you need the conditions to be slightly basic for that the protection to happen and that activation to happen. In other situations, you need the solution to be acidic. So now you're changing the pH, constantly, and that can be a little bit inconvenient if you keep this in solution the whole time. The other thing too is that the byproducts that you're generating, they could potentially get involved in some of the reactions, especially after activating the carboxylic acid with DCC. So you would have to constantly be doing extractions to separate your product from the other materials. And in some cases, you might even have to do column chromatography just to fully separate them. So this will become, even for this tripeptide, this could become a very laborious thing, right? So although on paper this looks kind of nice, for the most part, it's not a great thing. But there's one solution, and the solution is to try to do this in a heterogeneous manner, meaning that if we can make it so that our peptide is kept outside of solution while the byproducts remain in solution, then we can easily just wash away the solution without having much of an issue. And incidentally, that is where our good old friend Merrifield ended up doing. The technique is actually rather interesting because what you do is you take your amino acids and right out of the gate, you protect the amino groups of all of them. So you just put FMOC on all of them. And each of these amino acids, by the way, are in separate solutions. So they're not together yet, but you still protect them at the amino group. And then what you do is you immobilize the very last amino acids of your sequence, which in our case, that will be asparagine, by placing them on a resin. And the resin itself is simply going to be, a polymer that happens to have, every so often, a component, an alkyl halide component that's primed for an SN2 reaction. So all you technically do is you introduce your last amino acid that has the carboxylate or carboxylic acid group available, intact, and protected, and you have it react with the solid support that contains the alkyl halide. And this is literally just an SN2 reaction. That SN2 reaction will install via technically an ester the last amino acid to this solid state support. And I'll state it again, the solid state support never dissolves in your solvent, so it remains as a solid the whole time through. Okay, so here's what happens. Once you have added the last amino acid to the solid support, now you remove FMOC. So you basically now add piperidine, that will remove FMOC altogether. And now that you have the activated, or technically the free amine, you simply introduce the second amino acid along with DCC to activate the carboxylic acid of the second to last amino acid. That will now incorporate alanine, to the amino group of asparagine, right? So we're basically going backwards right here. All right, and then at that point, you simply, you'll have to wash this, wash the solid support, but then you'll add piperidine to remove FMOC. You'll also wash this stuff, and then you will add the last amino acid along with DCC to activate the carboxylic acid of aspartic acid, and you will simply end up generating the last peptide bond. So the last thing, of course, it is to protect that the last amino acid, get rid of FMOC by adding piperidine, and finally you add acids to remove the full peptide from the resin. And then what will happen is that the resin will simply be still a solid, but the amino acid is now dissolved in solution. So now you can collect the amino acid, in your filtrate. And to kind of give you a full illustration of how this technically will work in the lab, well, simply you will have, like a frit, with a coarse filter, that you can hook up to a vacuum, right? And so you have your solid support on this frit. Okay, so this is your solid support. Then you add the last amino acid, which in our case was asparagine, and you mobilize it just by having those two groups reacting with each other via the SN2 reaction. Um, then what you do after, the required time, you have to wait a few minutes for this to be done. But right at that point, you just filter all of the solution, and then you wash it. You add, some extra water to wash it, and then you filter that off as well. but your solid support along with your immobilized asparagine amino acid is now present up here. Okay, so now that's what we have as the resin on your filter. So then what you do next is you add piperidine to remove the FMOC group that's in your solids support. You filter that after the required time, then you wash the solid again and you filter that. And once that's done, you have that free amine group of asparagine. And so now you're ready to add the second to last amino acid, alanine, along with DCC. And you let those components be in contact with each other for, a few minutes. And once that, you know, incubation time, if you will, is done, you simply filter the material, right? And at this point you will have now the two amino acids connected to each other. Alanine is now connected to the amino group of asparagine. So you just wash that, you filter it, you wash it, and once that happens you can add piperidine to remove the FMOC group of alanine. And once again, you filter that material after the required time, you wash it and you filter that as well. And now you're ready to add to the solid support the first amino acid of the sequence along with DCC. So you add those two components together. You let it react for the required time, which will now install aspartic acid onto the amino group of alanine. So then you filter that, you wash it, you add water, you wash it. And after you do that, you obviously remove the filtrate. You get rid of the filtrate each time. So, you don't keep accumulating it, you just get rid of it. And this last step is important because you want to get rid of all that crap so that now you are ready to remove the stuff from the solid support. So the first thing will be add piperidine to remove FMOC, and then you filter it, and then you get rid of that crap, filtrate as well. You still have your peptide on the resin, but here you add your aqueous acid, and ideally you've gotten rid of this filtrate, so you should have nothing in here. But you add your hydrochloric acid, you know aqueous hydrochloric acid onto your mixture, and that will allow you to break open that ester bond back to a carboxylic acid. And so what will happen is that up here on the filter, you will have the solid resin now without the amino acids. And your amino acid sequence that you've just synthesized will now be collected on your filtrate. So it's a very elegant, super simple technique. Obviously you can't do this with a full, protein, because proteins have hundreds and hundreds and hundreds of amino acids, bound together. But for simple oligopeptides, this is like the best, type of synthesis that you can do. You could do this whole tripeptide synthesis in one sitting, just by doing sequential washing, sequential filtrations, and sequential additions of reagents. So it's as elegant as it gets. And with that, we have concluded the topic of synthesizing proteins. So hope you enjoyed this particular lecture series. There might be more videos to come in the future, but for now, this is kind of the bulk of the story for amino acids from the point of view of OChem. So hope you enjoyed it, and catch you on the next series. Bye bye.